In the highly cited paper, Language Models Are Few-Shot Learners, Brown et al. From OpenAI detail a transformer model, which is a variant of the encoder-decoder neural network architecture that provides state-of-the-art zero-shot and few-shot performance in many language tasks, while also excelling at generating human-sounding text. This powerful model continues the slightly troubling, continuing trend of throwing data at a model and hoping it generalizes on its input, but is nevertheless an impressive achievement in the field of natural language processing. Traditionally, NLP systems have increasingly relied on pre-trained language representations to perform downstream tasks. For example, word vectors have been commonly used to feed input into various model architectures. Word vectors are a compression of variable-length alphanumeric strings into a semantically coherent fixed-length numerical representation. As you can see here, we have the word apple that is being translated into a 5-dimensional vector. Another approach that has been used in the past is to utilize hidden states of sequence models, such as recurrent or transformer neural network units, to perform various tasks directly. Now, this particular approach relies heavily on fine-tuning said model. Fine-tuning is a process in which a pre-trained model's parameters are adjusted for the specific task it's performing. For example, if a model aims to provide diagnoses for certain symptoms, it may be trained on a corpus of symptoms and their root causes. However, the authors contend, this type of paradigm restricts the applicability of language models, creates problems for the generalizability of such models over their domain, and is inconsistent with how humans process new information. Logically, this makes sense. If a model requires to be fine-tuned before being applied to a new language task, it loses a lot of its utility. Instead, GPT-3 relies on zero-shot, one-shot, and few-shot evaluation, where the numeric quantifiers represent how many examples are provided alongside a natural language description of the task. For instance, a one-shot evaluation of a model would only provide one example next to the prompt. And in all cases, no model parameters are modified, which is a significant difference compared to fine-tuning. GPT-3 follows a recent trend within the literature of utilizing more parameters to improve the performance of models. Here they jump from just a few billion parameters in GPT-2 to over 175 billion parameters spread across 96 different layers in GPT-3. This increase in parameters led to a massive improvement across zero-shot, one-shot, and few-shot tasks. As you can see in the graph, there is continuing evidence for the author's stated hypothesis that more parameters leads to higher performance and thus higher generalizability of language models. In turn, this model was trained on about 700 gigabytes of data pulled from sources including Wikipedia, Common Crawl, which is a project that scrapes web data specifically for research use, WebText2, which is OpenAI's proprietary dataset collected from the web, as well as Books 1 and 2, which is a book dataset. Note that one token corresponds roughly to one word, and that they trained over approximately 500 billion tokens. In order to prevent contamination of test data in their training examples, they attempted to utilize homegrown filtering tools to detect such usage and proactively stop that. However, there resulted in a few overlaps, which inflated later performance metrics. An interesting training detail here is that the batch size was kept large while the learning rate was quite small, meaning that the gradient updates were quite small every batch. Heavy usage of parallelism was required to prevent running out of memory given the model's size. Despite the model being trained and run on a large computing cluster developed by Microsoft. The model took about 5,000 petaflop days to train. The model also, speaking of performance, the model also did impressively well on datasets that involved the modeling of long-range dependencies of text, including Lambda and HelloSwag. But where the model shines, despite not having an explicit method for searching through the information it was trained on, is in closed book question answering, in which the model is asked about very broad factual knowledge. In fact, on one dataset, specifically Trivia QA, a few-shot approach slightly outperforms the fine-tuned state-of-the-art model, despite being much more generalized. One important trend to point out is that the model's increasing performance it can be attributed to the number of parameters increasing, underscoring the need for increased parameter count when performing open-ended tasks. And this theme of generalization continues when observing GPT-3's performance on NMT or neural machine translation tasks, in which it outperforms the state-of-the-art in French to English language translation and Dutch to English language translation. And for tasks like common sense reasoning, the model still comes short of the fine-tuned state-of-the-art, but still does surprisingly well. Quite surprising, however, is the model's performance on tasks such as arithmetic, word scrambles, SAT-style analogies, and generation of news articles based on a prompt, all of which are unlikely to be present in the training set, and thus are not affected by the aforementioned training data issue. One key finding to note, across these tasks is the success of the few-shot paradigm. Across arithmetic tasks, including low-digit addition and subtraction, the model performs well when given examples to replicate. An interesting counterpoint to this, however, is high-complexity arithmetic, at which the model performs extremely poorly. This is similarly the case when looking at a word scramble task, where simpler modifications of a word were much easier for a model, thereby indicating that this model is not perfect, but it does certain types of tasks pretty well. SAT-style analogies similar to Trivia QA seem to suggest that open-ended inference is best handled by higher parameter language models, something that GPT-3 is specifically focusing on. Upon further inspection of the news articles generated based on a prompt, this is where the model really shines. Notice the varied sentence structure and topical coherence of this sample article, as well as the matching of tone, as well as the matching of expected tone in a news article. However, there still remains a question as to whether these models are generalizing or not, given that they may have been trained on some of the very corpora they're being evaluated on. The authors describe this as data contamination and developed a novel method for detecting such problems in order to choose unbiased benchmarks for their model. But the authors themselves acknowledge that their efforts are incomplete. Finally, the authors conclude by discussing the broader societal impacts of their scholarship. One key concern was the potential usage of such research by mid to high skill threat actors to generate spam and misinformation. Brown et al. Concluded that no such attacks have been seen in the wild, and that there needs to be further research around incentive structures for using large language models to perform this kind of attack. Another prescient concern was the model's bias against various groups, including gender groups, religious groups, and ethnic groups. They found that the model expresses the biases that have been found in their dataset, from negative perceptions of African Americans to the mischaracterization of other groups. The authors believe that further research needs to be done on how to handle unsafe or inflammatory outputs by model. One of the key strengths of this paper is the depth at which the authors describe their training process, dataset selection, model performance, and the societal implications of their work. One key attribute that makes for good research based on my understanding of academic literature is the reproducibility of results. A few fields within academia have faced a reproducibility crisis, in which key results from the past few years have been impossible to reproduce by other researchers. I really appreciate the lengths the authors went through to provide all necessary information for a motivated researcher should they choose to reproduce these papers' results. Another key strength was the inclusion of the section discussing societal implications of their scholarship, something that is notably absent from many machine learning papers, including the original GPT-2 paper. Given the model's ability to be misused, I really appreciate that the authors considered and consulted with security experts on how threat actors may misuse their work. Focusing more on the content, I believe this paper is a groundbreaking result within the field of NLP, given the generality of the model across different tasks. It can quite literally do any language-based task reasonably well. I've also gotten a chance to use the API version of this model via their beta, and is phenomenal at producing realistic text with just one example. Here are some examples of generated text. In this particular example, the model was given an example of a congratulatory LinkedIn post and was told to generate its own based on a specific set of parameters. The bolded text that you can see is the prompt that was given to the model, and the regular non-bolded text is what it generated. And you can see that it generated perfectly and within the style of other LinkedIn posts that are on that platform. In the second example, GPT-3 was given a natural language description of an HTML-based user interface and was able to generate an interactive application that functions as expected. These and other usages of this model generated a lot of hype. With that being said, a key point of concern is accessibility of this architecture. Very few researchers and industry practitioners have access to a computing cluster of OpenAI size to train such a model on, making it very challenging to reproduce the exact results seen here, despite the author's efforts to provide all training details including learning rate and dataset sourcing. In fact, some critics of OpenAI point to the non-release of GPT-3 on moral grounds as a clear violation of the lab's mission to provide the fruits of their research to everyone. Additionally, the commercialization of the GPT-3 API, in which users can pay to generate text using GPT-3, did seem a bit suspect. Another key concern that I have about the results in this paper is an incomplete effort at removing contamination from the model's training dataset. While the authors did take great effort into detecting such issues, they explicitly stated in the paper they did not handle all cases of this happening, which may have artificially inflated performance on some of the metrics that they measured on. With all that in mind, I still think that the creation of this model is a net positive to work within natural language processing. In conclusion, GPT-3 is a general-purpose language model that excels at many different tasks and was designed to mimic the way humans generate text, which is via past knowledge and not domain-specific fine-tuning. This massive 175 billion parameter model was trained on a combined 730 gigabyte dataset of websites and books, and while the model performed worse than the state of the art in many tasks, it generally performed very well on language tasks, despite not being explicitly trained to do such tasks. And while the authors did face some issues with data contamination, they still strongly believe the model generalizes its input well. Finally, that the authors believe that safe use of this model and large language models in general is an important issue to study from an ethics and policy perspective. Based on the excellent performance of this model, it may be time to study GPT equivalents for non-textual modalities, such as image, video, or audio. One exploration of this exact concept and of relatively recent development out of OpenAI comes in the form of DALL-E. DALL-E uses the generalized language performance of GPT-3 specifically to the domain of image generation from natural language. However, there are still not any equivalents of GPT equivalents for video or audio domains. I would like to reiterate that this is a very exciting field of machine learning, and I cannot see wait to see what comes next. Thank you for listening, and I hope you have a great day.